Every device that draws power from an AC line has to pass conducted emission limits. Whether it's a drilling machine, a PC, or even your washing machine. To reach the limits, we have to apply a power line filter close to the AC connections. Filters might be built as a separate printed circuit board or come as a closed encapsulated system. In almost every case, a single component is not enough. We need at least one common mode choke, X capacitors, Y capacitors, and we have to decide how many of them and in which order to apply them. So the practical question is not whether we need a filter, the question is how many elements do we need and which of them. Often within EMC labs you will find filter design kits. Mine is the Würth Electronic Design Your EMC Filter Design Kit. Find the link within the description. This kit contains multiple empty printed circuit board filter boards and a set of components. 21 common mode chokes, 4 Y capacitors, 3 X capacitors. The idea of the board is that you build your proper EMC filter that fits the needs of your application. The problem, even with this small amount of elements, there is a huge variety of possible ways to build the filter. The board allows us to determine all possible filter circuits with just 4 element positions that gives us up to 1,760 different combinations. How do we find the best solution for our problem? The first step towards a systematic approach is always the same. We have to separate the common mode and differential mode disturbances. Only then a filter can be selected that matches the type of noise we are dealing with, instead of adding components over components and hoping for the best. Best to start with is to have a measurement without filter, and you know which filter attenuation you need to keep the limits. If not, make an estimation or use an oversized filter. That you have the chance to optimize the components if needed. To evaluate the filter circuits, I ran 3,520 simulations. If you are now wondering why so much and not 1,760, the attenuation of a filter has to be determined separately for common mode and differential mode. 2 simulations per combination, so twice the number of runs. Have you seen the outcome? On the left, differential mode attenuation over frequency for all combinations. On the right, common mode attenuation. The green arrow marks the combination with the highest average attenuation across the frequency range. But take care, all these simulations are performed with 50 ohm noise sources and automotive listens on the input side. And that brings me to the point I actually want to discuss. Does any analysis in a 50 ohm system makes any sense of that all? Almost every filter datasheet you will ever read shows insertion loss measured in a 50 ohm system. It is convenient and standard, but for example, a switched mode power supply is of course not a 50 ohm source. So I ran the simulations again. This time with source impedances that I consider to be closer to the reality. For the differential mode disturbance source, an inductive impedance of 10 nanohenry is used. My assumption here is that the line inductance dominates the behavior, and 10 nanohenry is certainly one on the low side. For the common mode disturbance source, a capacitive impedance of 80 picofarad is used. This one is based on intuition and experience and cannot be justified. It depends heavily on the geometrical layout of the system. But look at what happens. In both plots, a significant number of curves rise above the 0 dB line up to plus 20 dB. Positive values mean the filter is not attenuating the disturbances. it is amplifying it. The root cause is the interaction between the inductive and capacitive source impedance and the reactive elements of the filter. Together, they form a resonant circuit. At the resonance, the noise voltage at the output can be higher than it was at the source. This is not a simulation artifact. This is exactly the effect that shows up in the lab when a filter that looked excellent on paper makes the emission spectrum worse in a specific frequency band. Nevertheless, we have to start with one filter setup. So my advice is to choose a filter with high attenuation in the frequency range and you need, and with respect to the main dominant noise source. To make it easier to distinguish the individual filter combinations, we created an online tool that lets you filter the results and find the combination that fits your problem. How exactly it works, I will show you in the next video.